Now, we can move a little bit on. So what are the limits, what are the factors that do limit the operational ability of the aircrafts in terms of the G-force? Besides the airframe capabilities, the maximum load values of the G-force are also limited by the physiological capabilities of the pilot, because a human's ability to take the G-force is determined by these factors: the magnitude, the direction, the duration of exposure, the frequency of exposure, and the physical condition of the pilot himself. Because again, the G-force talks about how much force is applied by your weight. For example, if you have again a 5G, that means that you're experiencing a force that is 5 times your weight, which is a very large force, for instance. But also it depends, as you can see here, on the direction, right? So that depends on if it is 5Gs, for example, down. That means that the blood is going to be pulled from your head towards down the body. And if it is minus 5G, so it is, for example, in the other direction, then it's the opposite case, which is very dangerous for the pilots. And if it is lateral, then it's also the same, which is also very dangerous, by the way. And the frequency of exposure, that means, and in fact, the duration of exposure is much more important. So, for example, if this G-force is applied, for example, at a few seconds, then most humans are going to tolerate it. But if it is applied, for example, at a longer period of time, like, for example, in a dogfight where the pilot has to push himself to the limits, and, for example, this duration can be extended to more than a few seconds, so it can be like 30 seconds or 1 minute or a few minutes, and then this is going to be an entirely different story, right? And also the frequency of exposure, the physical conditions of the pilots. Here, there are certain training procedures which prepare the body of the pilot, for example, for experiencing a certain G, and that is going to increase his tolerance to high G forces and will increase the duration, and in this case, if it is a fighter pilot, then he will have a higher chance of surviving a dogfight, for instance, right? Now in this regard, also, a few solutions exist for increasing the pilot's endurance of high forces. These include, for example, changing his position in the cockpit, favoring a closer to the aircraft center of gravity and a lean back position. Now, why closer to the center of gravity? Because the further away from the gravity, when the aircraft is moving, the force, the G-force that is applied in a rotation, if something rotates, then the further away from the center, the more is going to be the distance that you're going to cover, and the more is going to be the force applied on you, right? And the closer to the center of gravity, the smaller is going to be your motion against the aircraft itself, and that is going to reduce the G-force, and also favoring a lean back position, because if you lean back while experiencing vertical G-force, is going to reduce the motion of blood from your head to down, and that is going to increase your ability to withstand the G-force in a little bit longer times. And finally, using the G-suits. The G-suits, or anti-G-suits, in fact, or how it is called? Yeah, anti-G-suits. So this is a suit that pushes against the body when the aircraft experiences G-forces, and therefore preventing the motion of blood from the head down, and therefore preventing, for example, loss of consciousness and other consequences of experiencing this kind of motion of blood, right? So it also increases dramatically the tolerance of the pilots towards the G-force. But also, apart from the pilots, as said from the beginning, the first and most important thing is the ability of the structure itself to withstand the G-force, right? Why? Because this force applied to the structure will also lead to stress, and there is a certain amount of the stress that the structure can take, and beyond that amount, there is a risk to break the aircraft off. For example, if the G-force is applied, for example, at certain direction or at certain location on the structure where we can exceed the values that are allowed for this type of structure. And you can talk a little bit also about the design requirements, which have also to do with the G-force and the airframe strength standards. So now let's see the design requirements for aircraft's airframe structure. So by the airframe, we mean, again, the structural part of the aircraft, which is the metallic part, if you like, the middle of the skeleton of the structure, right? So there are certain design requirements in order to ensure the aircraft's flight worthability, or how this is called, operationability, right? Or flight or airworthiness, right? So if the aircraft is airworthy, that means that it can fly. And in order to achieve that, we need to make sure that the the airframe structure can have the maximum task completion efficiency, the minimum structural weight with sufficient strength and rigidity, because as we have seen, the weight is the enemy number one for the costs of their flight, right? So the heavier the aircraft, the more expensive it is to fly it. And lowest possible life cycle costs complying with certification regulations, like, for example, the FAR for civil aircraft and so on. And the lowest possible life cycle costs can, for example, be achieved by striving to use as much as possible really solutions and off-the-shelf components. So off-the-shelf components is components really in the market, so you don't have to design it from scratch. You don't have to buy it, for example, from somewhere else. So if it is a ready off-the-shelf component, then that's going to be reducing the life cycle costs of the aircraft, rather than developing, for example, new technologies, unless existing solutions do not provide the required level of task mission efficiency, which is the number one requirement here, right? So there is a certain optimization here, whether we want to, for example, develop new solutions in order to have a better task completion efficiency, or we will, at the same time, we want to have lowest possible life costs because we have certain budget limits, right? And the second point here is quite clear: the minimum structural weight with sufficient strength and rigidity. This is a direct result of having the best structural design and the best structural materials possible in order to achieve the minimum weight, but at the same time, sufficient strength and rigidity, which is not quite very easy to achieve all the time. And the final point here, because we have, as we have seen in the first lecture, there is something called the aviation complex, and the aircraft is just a small part of it. In fact, there are some other parts, and the big players here is the regulation bodies, the bureaucratic bodies that form certain guidelines for having an aircraft that is worthy, right? And one of these, for example, is the FAA, the Federal Aviation Agency in the US, for example. We have also the aviation rules in Russia, the AP, so-called. Right, so these documentations, they provide some guidelines in order to have an aircraft that is going to be allowed to fly and allowed to be operationable legally, right? Now, airframe strength standards is part of these guidelines that have been seen here. And one of the main conditions of flight safety is sufficient airframe strength and stiffness, although it has to have minimum structural weights, as we have agreed before that. And all of these requirements are summarized and standardized, right? So standard means that it doesn't matter whether the aircraft is big, is small, is heavy, it has two engines, it has one engine. So these standards, they apply to a certain type of aircraft. For example, if it is a class A, class B, class C, we're going to see how these classes are classified depending on the mission profile of the aircraft, right? So all of these requirements are collected together in what is known as strength standards and other regulatory documents. So these documents, they set the general level or standard level of the airframe structural strength, including basic parts of the assemblies, as well as test conditions for identifying the strength. So for instance, there are certain design cases or flight cases, for example, taking off, maneuvering at certain trajectories, for example, entering the dive, exiting the dive. So all of these points in the flight of the aircraft are going to generate certain amounts of the G-force, right? And those amounts of the G-force is the design points of the aircraft for it to be worthy, for it to be operatable. It needs to pass tests in certain these specific points. So these standards, they set sufficient degree of strength of various parts of aircrafts, which provides an acceptable or low, so the lowest possible, in fact, failure probability of the structure and the specified conditions during flight, takeoff and landing, and some other off-design conditions as well, right? So there's certain off-design, so for example, light strike, bird strike, and some other things that do happen, not all the time, fortunately, but they do happen during the aircraft operation, and the aircraft is supposed to withstand a certain amount of stress that is a little bit higher than the operational stress that the aircraft is exposed to every day. And operational, which means the maximum load during operation loads on the aircraft main parts. Safety factors, which demonstrate the ratio of the ultimate destructive load to the operation load of the main parts of the components of the airframe structure. So that means that the structure needs to have a certain safety margin, right? So it needs to have a certain reserve strength that is not used all the time, right? So it needs to have a certain margin. So for example, the load that is acting all the time needs to be a little bit far away from the destructive load, because that's the only way to achieve, for example, flight safety or a low failure probability, right? So to reduce the failure probability, we need to have a certain structure that is a little bit heavier than it should be, right? So it is a little bit stronger than it should be. Uh, Strength standards according to maneuvering characteristics allow us to divide all aircrafts into 3 basic classes: Class A, Class B, and Class C. So depending on the G-force that the aircraft is going to be experiencing, the aircraft can be maneuverable, like for example Class A, for fighters, aerobatic aircrafts. So these guys are not designed for long range and heavy payload, so they need to withstand a very high operational level of G-force, which can be up to, for example, 8, 9, and in fact for fighters up to 12, right? So if the aircraft is designed to fly at very high G-forces regularly on a daily basis, then its structure needs to withstand an amazing amount, a crazy amount of active loading, which can be 12 times its weight, or 8 times, for example, here, the operational maximum G-force. So this is a Class A aircraft, and this Class A means that it will have a certain design guidelines and a certain strength standards, right? Now, Class B aircraft, which is limited maneuverability jets, for example, smaller jets, which can have operational maximum G-load of 3.5 and up to 5. So this is still quite a very maneuverable aircraft, but it's not a fighter and not an aerobatic fighter, which can have, for example, 12 or 9 G-force, but for example 5. So this is, for example, tactical bombers, attack aircraft, tactical reconnaissance aircraft. So it is still a military aircraft that needs to get, for example, as fast as possible away from a certain hazard, danger, or some enemy region. So it is not a fighter, but it still can be experienced, and it needs to be designed to withstand certain type of loads, so up to 5 G-force. And finally, non-maneuverable airplanes. These are the long-range, heavy payload aircraft like transport aircraft, long-range bombers, passenger airliners. So these guys, they are not usually supposed to experience very large G-forces, and they are designed to experience a maximum of 2.5. In fact, if it is an airliner, then 2.5. If it is a military aircraft, like for example, military transport or long-range bomber, then it's a 3.5, right? So in this case, the allowable airframe strength is determined by loads during turbulence, right? So the turbulence is the worst case scenario, right? So if in this case turbulence is relatively not a big problem, then for this case, because the aircraft is not designed to fly at very high G-loads, then turbulence is basically the worst case scenario where you have the G-force is there is a risk for surpassing these kind of values. And finally here we have the stiffness standards, which regulate the allowable deformation of aircraft parts, because when we apply a certain force at a certain structure, it will deform, it will stress, and it will switch its shape, right? And the allowable deflections, angles of twist, as well as the value of critical speed limits and aeroelastic phenomena like flutter, buffeting, and divergence. We're going to explain all of these words a little bit later in our course, or maybe in subsequent courses of aircraft design or strength of aircraft structures in particular. And so these standards, they regulate the maximum speed, for example, allowable for the aircraft based on the margin of flutter, right? So there is a certain margin when the vibrations of flutter begin and the aircraft can break off because of these vibrations, right? So the margin of flutter is going to determine, according to these stiffness standards, the maximum allowable flight speed. And finally, here we have the airframe testing, which is also a part of the strength standard. So it is what determines the aircraft's airworthiness, whether it is airworthy or not. So we have to test it on the ground and in flight. And there are certain types of tests. We can see here the static, dynamic, and flight tests, right? So static, we need to for determining the failure or the maximum strength of the aircraft. The dynamic carried out to evaluate, for example, structural strength under certain dynamic loads which change over time, and flight tests, which are used to determine the flight loads together with the flight characteristics, checking the existence of dangerous vibrations and flight regimes which are in the real life, right? So which is in the real operational life of the aircraft. So that's basically it for today's lecture. We're going to see the aircraft balance in